March 5, 1944. Midnight over the Burmese jungle. A canvas and plywood glider cuts loose from its tow plane at 3,000 feet, its cargo bay packed with 5,000 pounds of steel. Inside, strapped to reinforced floor mounts, sits a Clark CA-1 Bulldozer, compact as a jeep but built like a tank. The glider pilot peers through darkness at a clearing that shouldn't exist, a space hacked from virgin jungle by advance teams just hours before. Trees loom on all sides. There's no margin for error. Impact. The glider slams into earth, nose crumpling, wings shedding fabric, wooden spars splinter with sounds like rifle fire. The fuselage slides forward through mud, decelerating from 70 miles per hour to 0 in 3 seconds. Forces that would crush a man hammer through the airframe. And then, silence. Engineers rush the wreckage. They unbolt the cargo doors, lower the ramp. The bulldozer's engine coughs, catches, roars to life. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within minutes, it's grinding forward, blade down, pushing jungle debris aside, carving runway from wilderness, while Japanese forces 3 miles away have no idea. American engineers are building an airfield behind their lines. This wasn't supposed to work. Every military engineer who'd examined the problem said the same thing. You cannot drop construction equipment from aircraft and expect it to survive. The forces involved would destroy the machinery before it touched ground. The Clark CA-1 weighed 5,000 pounds, more than a standard Jeep. The bulldozer blade added another 600 pounds of cast steel. Landing forces would snap hydraulic lines, crack engine blocks, twist the frame into scrap metal. Yet, by dawn on March 6, 1944, more than 30 bulldozers had landed in that Burmese clearing. Within 24 hours, they'd carved a functional airstrip 300 feet wide and 5,000 feet long. C-47 transport planes were landing with reinforcements before the Japanese even understood what was happening. The man who made this possible wasn't a general or a combat engineer. He was an industrial designer from Michigan who'd spent the 30s building equipment for logging companies, and his name has been forgotten by history. Understanding why this achievement seemed impossible requires understanding the physics of glider crashes and the desperate logistics situation that made the impossible necessary. By early 1943, Allied forces were fighting on multiple fronts, where traditional supply lines couldn't reach. In the Pacific Theater, island-hopping campaigns required rapid seizure of Japanese-held airfields. In Burma, British Chindit forces were operating hundreds of miles behind Japanese lines, with no ground access. In both theaters, the bottleneck was the same. You could drop paratroopers, but you couldn't give them the heavy equipment needed to construct airfields, fortifications, or supply depots. Engineers needed bulldozers, graders, compactors, the machinery that turned rough ground into functional bases. But construction equipment was heavy, built for durability, not portability. A standard Caterpillar D7 bulldozer weighed 15 tons, far too heavy for any glider then in service. Even smaller dozers designed for agricultural work weighed 8 to 10,000 pounds and stood too tall to fit inside a glider's cargo bay. The U.S. Army Corps of Engineers faced a brutal choice: drop airborne troops without construction support and watch them struggle for weeks to build what bulldozers could create in days, or abandon airborne operations in favor of slower conventional advances. Neither option was acceptable. Speed was everything in 1943. German forces in Europe were being pushed back but could still reinforce positions if given time. Japanese defenses in the Pacific were formidable, their positions dug into coral and jungle with defensive works that required months to reduce through conventional assault. Every day saved in establishing forward air bases was a day gained in the race to victory. So engineers at Wright Field in Ohio set specifications that seemed like wishful thinking. They needed a bulldozer that weighed less than 4,000 pounds, stood no taller than 5 feet, could fit through a glider cargo door, possessed enough power to grade landing strips and fill bomb craters, and most impossibly, could survive crash landings that destroyed the aircraft carrying it. The specifications went out to American manufacturing companies in late 1942, with a request for proposals. Most companies didn't bother responding. The requirements violated fundamental principles of construction equipment design. Build something light enough to fly, and it wouldn't have the power to move earth. Build it compact enough to fit in a glider, and there'd be no room for an engine with sufficient torque. Build it to survive 70-mile-per-hour impacts, and you'd add so much protective structure, the weight would exceed glider capacity. Build it cheap enough to be expendable, and it would fail within hours of operation. Every traditional engineering approach led to impossible contradictions. Clark Equipment Company of Battle Creek, Michigan, saw the specifications differently. Clark had built its reputation making forklift trucks and small industrial tractors for warehouses and lumber yards. They understood compact equipment in ways that construction machinery manufacturers didn't. More importantly, their chief engineer, Maurice Zollinger, had worked with the U.S. Forestry Service, developing trail tractors, specialized machines designed to work in spaces where full-size equipment couldn't reach. When the Army's request for proposals arrived, Zollinger recognized an engineering challenge he could solve, not by making equipment lighter, but by rethinking what a bulldozer needed to be. The key insight was temporal. Standard construction dozers were built for continuous operation on major projects, highways, dams, large-scale earth-moving that might last months or years. Airborne engineers didn't need machines that could work 8-hour shifts for months. They needed equipment that could clear runway debris, fill shell craters, grade landing strips, and push aside destroyed aircraft in 48 to 72 hours, just long enough for heavier conventional equipment to arrive by sea or ground transport. This changed everything. Zollinger stripped away every component that wasn't essential for short-term intensive work. The engine came from Hercules Motors, a 4-cylinder flathead gasoline engine producing just 30 horsepower, compared to the 80 to 120 horsepower of standard construction dozers. 30 horsepower sounds inadequate until you calculate power-to-weight ratios. The CA1 weighed 5,000 pounds, complete with blade and tracks. A Caterpillar D4, the closest conventional equivalent, weighed 12,000 pounds with similar engine output. The Clark had better power to weight than machines twice its size. The transmission was direct drive, 4 forward speeds, 1 reverse, no torque converter, no power takeoff systems, no auxiliary hydraulics for attachments the machine would never use. The final drive used automotive-style differentials and axles, instead of the massive enclosed track drive systems standard on construction equipment. This saved 800 pounds immediately. Tracks themselves were narrow, just 12 inches wide, fabricated from manganese steel with curved grousers welded at specific angles for traction in mud, sand, and coral. The blade was a simple 7-foot curved steel plate mounted on pivot arms with a single hydraulic cylinder for raising and lowering. The entire machine measured 9 feet long, 5 feet 2 inches wide, and 4 feet 9 inches tall, small enough to roll through a Waco CG4, a glider's cargo door with 8 inches of clearance on each side. It could turn in its own length, climb a 45-degree slope, and push 3,000 pounds of material with the blade. Fuel capacity was 12 gallons, enough for 8 to 10 hours of continuous operation. Top speed was 4 miles per hour, slower than a man could jog. But speed wasn't the point. The point was arriving intact and functional. But size and weight were only part of the problem. The real engineering challenge was survival. And this is where Zollinger's background in forestry equipment proved crucial. Trail tractors for the Forestry Service operated in conditions that would destroy conventional equipment. Steep slopes, fallen logs, hidden rocks, constant abuse. They were built not with heavier components, but with intelligent placement of critical systems and sacrificial protection for vulnerable parts. Zollinger applied these principles to designing a bulldozer that could survive forces no construction equipment had ever been asked to withstand. A glider landing wasn't a controlled descent. It was a barely arrested crash. Pilots aimed for the flattest ground available, but in combat conditions, flat was a relative term. Burma jungle clearings had tree stumps hidden in tall grass that could tear a glider apart. Pacific Island beaches had coral outcroppings that punched through fuselages like fists through paper. European fields had drainage ditches, stone walls, and defensive obstacles deliberately placed to destroy gliders. Aircraft hit these obstacles at 60 to 70 miles per hour with no engine to adjust course, no ability to abort, no second chance. When a 5,000-pound bulldozer experiences that kind of instantaneous stop, Newton's first law applies with brutal efficiency. The dozer wants to keep moving forward at 70 miles per hour, while the glider around it disintegrates from deceleration forces. The inertial loads are enormous, over 25,000 pounds of instantaneous force. Standard cargo tie-downs, rated for 5,000 pounds, would snap like thread. Reinforced straps rated for 10,000 pounds would rip their anchor points out of the glider floor before the fabric could even finish tearing. Chain would hold, but the sudden jerk would shatter engine mounts and crack the frame. Clark's solution was elegantly simple. Don't fight inertia, manage it through progressive energy dissipation. The CA-1 was secured inside gliders using a system that engineering textbooks wouldn't describe for another 2 decades. 4 main steel cables, each 3/4 of an inch in diameter, connected the dozer's frame to reinforced hard points built into the glider's structural members. But these weren't rigid connections. The cables ran through heavy-duty steel coil springs rated to compress under specific shock loads. During normal flight, the springs held the dozer firmly in place with no movement. During a crash, the springs compressed progressively over fractions of a second, absorbing kinetic energy that would otherwise transfer directly to the bulldozer. The glider floor beneath the dozer wasn't standard plywood. It was a laminated sandwich construction. Hardwood beams running longitudinally, cross-braced with softer wood that had specific crush properties, topped with 3/4-inch plywood. The entire assembly was designed to compress during impact, not catastrophically but in a controlled, progressive failure. When the glider hit ground at 70 miles per hour, the floor absorbed the first wave of shock by deforming downward. The dozer dropped several inches as supporting beams crushed in sequence, each beam failure extending the deceleration time by milliseconds that accumulated into survival. Wooden blocks positioned strategically around the dozer's blade and engine compartment acted as sacrificial bumpers. These weren't simple cushions. They were engineered crush zones, hardwood blocks with grain oriented to fail in specific patterns under impact. During a severe crash, these blocks would shatter in sequence, each fracture absorbing energy through the work required to break wood fibers. The physics were straightforward. Kinetic energy must go somewhere when motion stops. By designing components that would break in controlled ways, Clark ensured that energy went into destroying expendable wooden blocks rather than expensive hydraulic cylinders or irreplaceable engine castings. The engineering was sound in theory. Testing would prove whether theory matched reality, and the testing would be more brutal than anything the bulldozers would face in combat. Wright Field, Ohio, became the proving ground in January 1943. Clark delivered the first 2 CA-1 prototypes for evaluation. Army Air Force's engineers were openly skeptical. The machines looked fragile, too small, built from components that seemed scavenged from agricultural equipment and automotive junkyards. One engineer noted in his report that the bulldozer appeared to be constructed of parts catalog surplus rather than purpose-built components, which was essentially accurate. Zollinger had deliberately used off-the-shelf parts wherever possible to enable rapid production and field repair. The testing protocol was specifically designed to destroy the dozers, to prove the concept impossible. Engineers loaded each machine into a CG-4A glider, secured it according to Clark's specifications, towed the glider to 1,500 feet behind a C-47 transport, released it over a designated crash zone, and instructed pilots to make the hardest landings physically possible. These weren't gentle training approaches or simulated emergency procedures. Pilots were ordered to dive the gliders in steep descent, to maximize velocity at impact, to hit the ground like rocks dropped from height. The goal was destruction, not validation. The first test on January 23, 1943, was almost anticlimactic in its success. The glider came down at maximum descent rate, hit the frozen Ohio field at 72 miles per hour, and disintegrated spectacularly. The nose section folded back like paper, wings collapsed inward, shedding fabric and splintering spars. The tail section broke free and tumbled across the field. The entire event lasted perhaps 3 seconds from initial impact to final rest, and the sound of tearing wood and snapping steel cables echoed across the test range like sustained thunder. Recovery crews waited for the dust to settle, then approached the wreck, expecting to find a demolished bulldozer, a twisted frame with engine torn loose, hydraulics ruptured, blade bent into scrap metal. Instead, they found the CA-1 sitting upright amid the wreckage, held in place by steel cables still attached to fragments of glider structure. The wooden crush blocks had shattered as designed. The floor assembly had compressed exactly as predicted. The springs in the cable system had bottomed out but hadn't failed, and the bulldozer itself was intact, every critical component still properly mounted. They disconnected the cables, checked fluid levels, examined the blade hydraulics. Everything checked out. One engineer pulled the starter cord. The Hercules engine fired on the first pull. They drove it out of the wreckage, circled the crash site twice, and put it immediately to work grading the test field. The bulldozer that had just survived forces that destroyed the aircraft carrying it was clearing debris from its own crash site 15 minutes after impact. The second test, 3 days later, introduced calculated complications. Engineers instructed the pilot to aim for a drainage ditch that crossed the landing zone, to hit it deliberately at an angle that would maximize asymmetric loads. The glider came down at full velocity, one wing catching the ditch edge as designed. The impact was vicious. The wing that hit the ditch crumpled instantly, spinning the fuselage sideways through 90 degrees while still moving at highway speed. The glider cartwheeled once, completely inverted, before slamming down on its opposite side and sliding another 100 feet through frozen ground. The CA-1 tumbled inside the disintegrating cargo bay like a stone in a washing machine. The steel cables stretched to their absolute limits, springs compressing fully, then partially releasing, then compressing again as the glider tumbled. When the wreckage finally stopped moving, engineers found the bulldozer on its side, half buried in torn canvas, shattered wood, and twisted steel. The entire left side of the fuselage had torn away. The cargo compartment no longer existed as a defined space, just a debris field with a bulldozer visible in the center. Recovery crews used another tractor to pull the CA-1 upright, cleared debris from the tracks and engine compartment. The blade hydraulics had lost pressure from a severed line, easily repaired with a spare hose. One track had derailed when the dozer tumbled but could be reset in minutes using standard track tools. The engine started on the second pull. Within 20 minutes, the dozer was operational, moving under its own power, fully functional despite having experienced forces that would have totaled any conventional construction equipment. Test after test through February and March 1943 produced similar results. Engineers deliberately created worst-case scenarios. They overloaded gliders beyond rated capacity to increase impact velocity. They instructed pilots to land in crosswinds that sent gliders ground looping, spinning like tops across the field. They positioned obstacles, simulated tree stumps and post barriers, in landing zones to guarantee collisions. They even fired live ammunition at gliders during approach, perforating wings and fuselage with simulated flak damage, then ordered pilots to land the damaged aircraft at maximum speed. The CA-1 bulldozers survived everything. Springs failed occasionally, but the backup cables held. Cables sometimes snapped, but the secondary restraint system caught the load. Wooden crush blocks shattered in every test, exactly as designed, absorbing energy through progressive destruction. Hydraulic lines ruptured when impacts exceeded design limits, but the hydraulic system was so simple that field repairs took minutes. Engine mounts flexed but never tore loose. Tracks occasionally derailed but reset easily. The frame, the critical structural element, never cracked, never bent beyond tolerance, never failed. By March 15, 1943, Wright Field engineers had conducted 27 crash tests. 23 bulldozers had emerged operational. 4 had sustained damage that required more than field-expedient repairs, but even these were repairable with replacement parts, not total losses. The survival rate was 85% under conditions deliberately designed to guarantee failure. If you find this story engaging, Please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Army Quartermaster Corps could no longer deny the mathematics. Clark's design worked. On April 2, 1943, the War Department issued Contract W906QM1843 for 800 CA-1 airborne bulldozers at $12,500 per unit, total contract value just over $10 million. Delivery schedule required the first units by August, with full production completion by January 1944. Clark Equipment Company had 4 months to scale from prototype to mass production, and Maurice Zollinger had 4 months to transform a hand-built experimental machine into something that could be manufactured at industrial scale. This created challenges as significant as the original design. Building 800 precision machines in 8 months required component standardization, assembly line manufacturing processes, supplier coordination across multiple industries, and a workforce that understood both automotive fabrication and heavy equipment construction. Clark's Battle Creek facility underwent complete reorganization. The company hired production engineers from Ford and General Motors who understood assembly line work. They brought in welders from Great Lakes shipyards who could work with the specialized steel alloys required for the bulldozer frame. They recruited mechanics from Caterpillar and International Harvester who knew construction equipment. Each CA-1 required approximately 2,300 individual parts sourced from suppliers across the Midwest and East Coast. Hercules Motors in Canton, Ohio, provided engines, shipping 4 units per week initially, ramping to 12 per week by September. Timken in Canton supplied specialized bearings for the track bogies. Warner Gear in Muncie, Indiana, manufactured the transmissions. Automotive suppliers throughout Michigan furnished axles, steering components, brake assemblies, and hydraulic cylinders. Clark manufactured the frames, blade assemblies, and track systems in-house at Battle Creek. The frame fabrication was particularly complex. Each frame started as 42 feet of 3-inch square steel tubing with 1/4-inch walls, cut into precisely measured sections, then welded into a rectangular structure measuring 9 feet by 5 feet with internal cross-bracing. Every weld had to be perfect because frame failure in the field meant complete loss of the machine. Clark hired the best welders they could find and implemented quality control inspections that rejected frames for flaws that conventional construction equipment would accept. The rejected frames were cut apart and the steel recycled, an expensive process but necessary to maintain the strength-to-weight ratios Zollinger's design required. Assembly time for a complete unit was 16 hours from first component to finished machine, but that 16 hours represented only the final assembly. Sub-assemblies, frame fabrication, engine preparation, track construction, and component testing added another 40 hours of labor per unit. Total manufacturing time was approximately 56 hours of actual work, spread across multiple workstations and 3 shifts running 24 hours per day. Production peaked at 5 units per day in November 1943, dropping to 4 per day during December, when quality issues with a batch of hydraulic cylinders forced temporary suspension of final assembly while defective components were replaced. The first combat-ready CA-1 bulldozers left Battle Creek by rail on August 12, 1943, destination San Francisco for shipment to the Pacific Theater. Another batch shipped to Norfolk, Virginia for transport to the European theater. A third group went to India via convoy, a 6-week voyage around Africa to avoid Mediterranean submarine threats. By January 1944, approximately 650 CA-1 bulldozers had been delivered to military units worldwide. The remaining 150 units would follow by March. Meanwhile, tactical planners were developing employment doctrines for airborne construction equipment. The concept was revolutionary in its compression of traditional military timetables. Standard procedure for establishing forward air bases required ground forces to capture territory, engineers to survey and clear the site, heavy equipment to arrive by ship or rail, then weeks of construction before the field was operational. Airborne delivery collapsed this timeline into hours. Drop engineers and dozers simultaneously, construct minimally adequate landing strips while infantry secured perimeters, establish forward supply bases within 1 day of landing. This would give Allied forces unprecedented operational tempo, but doctrine and reality required validation through combat. Theoretical concepts look elegant on paper, but warfare has an inconvenient habit of exposing assumptions that don't survive contact with actual conditions. The first combat test would come in Burma, and it would be far more complex and dangerous than anything Wright Field had. Simulated. Operation Thursday, March 1944. British Brigadier Ord Wingate commanded the Chindits, officially designated Special Force, long-range penetration units designed to operate deep behind Japanese lines in Burma. Wingate's operational concept was audacious. Establish fortified strongholds in enemy territory, supplied entirely by air, from which columns would raid Japanese communications and supply lines. But supply by air required landing strips capable of handling C-47 transport planes, and landing strips required bulldozers. Jungle didn't magically transform into graded runways through infantry labor alone. The plan called for glider-borne forces to seize 3 clearings deep in Japanese-held territory: Piccadilly, Broadway, and Chowringhee, named for famous streets in London, New York, and Calcutta. These clearings were barely visible from aerial reconnaissance, surrounded by jungle that concealed enemy positions, accessible only by air, 300 miles behind Japanese lines, with no possibility of ground reinforcement. The gliders would carry engineers from the 900th Airborne Engineer Aviation Company, American specialists trained specifically for rapid airfield construction, along with 27 CA-1 bulldozers, 4 graders, and support equipment. On the afternoon of March 5, 1944, hours before launch, reconnaissance photos revealed that Piccadilly had been blocked with logs, rendering it unusable. Japanese forces had either discovered the planned operation or, more likely, had been conducting logging operations in the clearing by coincidence. Either way, half the landing zones were now compromised. Wingate considered cancelling the entire operation. British General William Slim, commanding 14th Army, made the decision to proceed using only Broadway and Chowringhee. The concentrated force would be more vulnerable to counterattack, but the mission was too critical to abort. At 6:12 p.m. on March 5th, the concentrated force would first gliders lifted from Lalaghat airfield in Assam, India. Each C-47 Skytrain towed 2 gliders, a configuration that pushed the transport planes to their performance limits. The double tow reduced the number of tug aircraft required but created dangerous conditions. The C-47 engines strained against double the normal load, overheating during climb-out. The tow ropes, each 350 feet long, tangled when gliders didn't maintain precise spacing. During the 3-hour flight to Broadway, several tow ropes parted from overload, sending gliders spiraling down into the jungle. Others released when tug aircraft engines overheated to dangerous temperatures, stranding gliders too far from the landing zone to reach it. Brigadier Michael Calvert, commanding 77th Brigade, was in the lead glider heading for Broadway. He'd arranged code words to be radioed back to India. Sawyer Link meant trouble, abort further gliders. Pork sausage meant success, send everything. At 2:30 a.m. on March 6th, Calvert's glider cut loose at 3,000 feet over what maps indicated was Broadway. The pilot could see nothing, just darkness and treetops barely visible against slightly lighter sky. Pathfinders on the ground had marked the clearing with kerosene lanterns, dim firefly lights that might be the landing zone or might be Japanese attempting to lure gliders into a trap. The pilot had no choice. He committed to the approach. What happened next became one of the most chaotic and costly glider operations of the war, and it exposed truths about airborne operations that no training exercise could reveal. The clearing was smaller than photographs suggested, perhaps 200 yards wide by 600 yards long, and it wasn't clear. Tree stumps dotted the ground, massive teak stumps from logging operations, hidden in elephant grass that grew 6 feet tall. The pathfinders had landed hours earlier and attempted to mark obstacles, but darkness and time constraints limited what they could do. The first glider hit a stump at 70 miles per hour, and disintegrated, killing everyone aboard. The second cleared the stumps but landed long, crashing into trees at the far end of the clearing. The third landed successfully. The fourth collided with the wreckage of the first glider, its wing shearing off, sending it cartwheeling into the jungle. The fifth landed, struck a hidden stump during rollout, nosed over, and crushed the cockpit. Two more pilots saw the carnage and attempted to overshoot the clearing, but without engine power, their gliders stalled and fell into the jungle. By 3 a.m., 12 gliders had landed at Broadway. 5 were total wrecks with all occupants killed. 4 were severely damaged with casualties. 3 had made survivable landings. 23 men were dead, 30 were injured. And the operation had barely begun. Brigadier Calvert, who'd survived his glider's landing by luck and the skill of his pilot, surveyed the situation and made a decision that seemed insane, but was actually brilliant. He radioed Sawyer Link, stopping further gliders, but didn't abort the operation. He needed time to clear the landing zone, to remove wrecked gliders and mark the hidden stumps that were killing his men. The survivors went to work in darkness. They had flashlights and kerosene lanterns, no powered equipment yet because most of the dozers were still in India waiting to be towed in. Engineers marked stumps with white cloth torn from parachutes. They dragged wreckage to the edges of the clearing using mules and raw manpower. They pulled wounded from crushed gliders, performed emergency medical treatment in the dark, with Japanese positions unknown and potentially very close. By dawn on March 6th, they'd cleared a strip roughly 400 feet long, just barely adequate for another wave of gliders. At 6 a.m., Calvert radioed pork sausage. The second wave launched from India. This time, pilots towed single gliders rather than dangerous double tows. The flight took 3 hours. At 9 a.m., the first glider of the second wave cut loose over Broadway. The pilot could now see the clearing in daylight, could see the marked stumps, could choose his touchdown point. He landed successfully, then another, and another. By 10 a.m., 20 gliders had landed, most successfully. 23 CA-1 bulldozers were on the ground, and this is where the entire operation transformed from disaster into triumph. Engineers fired up the dozers immediately. The Hercules engines started easily despite the flight, despite the crashes, despite hours sitting in glider cargo bays. Operators drove the dozers into the clearing, blades down, attacking the problem that had killed 23 men hours earlier. They attacked the tree stumps that aerial reconnaissance had failed to identify, that pathfinders in darkness couldn't mark, that glider pilots in the dark couldn't avoid. The stumps were massive, 4 to 6 feet in diameter, teak wood as hard as steel, roots spreading 10 feet underground. A conventional approach would have been to dig around each stump, cut roots, and pull stumps with heavy equipment. The dozers didn't have time for conventional approaches. Operators drove straight at stumps, hit them blade first at full throttle, backed up when the blade climbed the stump face, repositioned, hit the stump from a different angle. The 5,000-pound dozers, with their compact frames and low centers of gravity, generated enormous pressure at the blade edge. They couldn't push stumps over, but they could rock them, could break roots through repeated impacts, could lever stumps out of the ground through sheer persistence. When brute force failed, engineers attached chains to stumps and dozers, using mechanical advantage to amplify pulling force. When stumps still wouldn't budge, British Royal Engineers who'd landed with the gliders attached explosive charges. Small-shaped charges positioned to blast through, roots without cratering the ground. The explosions cracked root systems. The dozers pulled stumps free. Each stump removed opened another 50 feet of usable runway. By noon on March 6th, 22 hours after the first gliders had landed, engineers had cleared a strip 200 feet wide by 2,000 feet long. It wasn't pretty. The surface was rough, studded with smaller stumps that had been cut flush with ground level, marked with holes where larger stumps had been removed. But it was flyable. Light aircraft could land and take off. That afternoon, a Stinson L-5 liaison plane landed, evacuating the most severely wounded. The pilot took off, cleared the trees by 50 feet, and proved the strip was functional. But 2,000 feet wasn't enough for C-47 transports. Wingate's plan required 5,000 feet minimum for safe operations, and the clearing needed to be graded smooth enough that heavily loaded aircraft could land without destroying landing gear. The Dozers attacked the expansion project with operators working 4-hour shifts around the clock. They pushed vegetation to the edges of the strip, creating windrows of cleared jungle that would later burn. They filled depressions with material pushed from higher areas, crude grading that nevertheless leveled the worst irregularities. They cut drainage ditches along both edges of the runway to prevent the monsoon rains, which could begin any day, from flooding the strip. The work was brutal, exhausting, constant. Operators sat on minimal seat padding, exposed to sun and insects, breathing dust and exhaust fumes, jolted by every irregularity the tracks crossed. The Dozers had no cabs, no protection, nothing between the operator and hostile jungle except 30 horsepower of American engineering. When operators became too exhausted to continue safely, they'd stagger off the machines, eat cold rations, drink water, collapse for 2 hours of sleep on the ground, then return to the Dozers for another 4-hour shift. By 6 p.m. on March 6th, just 36 hours after the first gliders landed, engineers had extended the strip to 3,500 feet long and 300 feet wide. Wingate himself flew into Broadway aboard the first C-47 transport to land, a symbolic gesture that proved the airfield was operational. The transport landed, taxied to a parking area the Dozers had cleared, shut down engines, and discharged troops and supplies. Before it took off again, engineers had already extended the runway another 500 feet. By midnight, the strip was 4,000 feet long. By dawn on March 7th, it measured 5,000 feet by 300 feet, fully operational, capable of handling continuous traffic. The numbers tell the story. In 48 hours, using equipment delivered by engineless aircraft, engineers had constructed a functional forward airbase in the middle of enemy-held jungle. C-47 transports began landing at intervals of 3 minutes, 16 landings per hour, operating continuously. By March 10th, over 9,000 troops had been flown into Broadway with supplies, ammunition, mules, and artillery. The airfield that wasn't supposed to exist had become a logistics hub operating at the intensity of a major airport. The CA-1 bulldozers that built Broadway remained in operation, maintaining the strip, expanding parking areas, clearing defensive positions, improving drainage as monsoon rains began in mid-March. The machines proved nearly indestructible under combat conditions. Several took small arms fire from Japanese patrols that infiltrated the perimeter at night. Bullets punched holes in the blade, dented the hood, covering the engine, even struck the operator's seat on one machine, but the simple mechanical design had so few vulnerable systems that combat damage rarely stopped operations for more than minutes. Japanese artillery fire was more dangerous. On March 13th, Japanese aircraft raided Broadway, dropping bombs that cratered the runway. Engineers had repaired the damage within 2 hours, using the Dozers to push displaced earth back into craters and grade the surface level. A direct mortar hit on March 18th destroyed one bulldozer completely, the first combat loss of a CA-1. The machine had been parked near an ammunition dump that detonated when the mortar round struck. The explosion scattered components across a 100-yard radius. Engineers salvaged parts and used them to repair other Dozers. By late March, Broadway had been operational for 3 weeks, an eternity in airborne operations. The stronghold had served its purpose, allowing Chindit columns to deploy throughout northern Burma, attacking Japanese supply lines and communications. On April 2nd, engineers began constructing a second airfield, codenamed White City, using lessons learned at Broadway. This time, they brought additional Dozers, pre-positioned fuel and supplies, and completed the entire project in 36 hours instead of 48. The success in Burma validated the airborne bulldozer concept completely and provided combat-tested doctrine for operations throughout the Pacific and European theaters. Within weeks of Broadway's completion, military planners were revising operational procedures worldwide. On Biak Island, New Guinea, in May 1944, American forces needed to capture and repair Japanese airfields to support the advance toward the Philippines. Engineers landed 20 CA-1 bulldozers via glider, using them to fill bomb craters and clear destroyed aircraft before conventional construction equipment arrived by sea. On Leyte in the Philippines, October 1944, the largest glider operation in the Pacific Theater delivered 30 bulldozers and supporting equipment. The dozers cleared beach obstacles, improved roads from the beaches to inland supply dumps, and constructed forward airstrips before Japanese forces could organize effective counterattacks. Each operation, compressed timelines, accelerated advances, gave American forces the initiative that comes from superior logistics. Then came Europe. D-Day, June 6, 1944. The Normandy invasion required massive engineering support immediately. Airborne divisions landing behind Utah and Omaha beaches needed to construct emergency landing strips, clear glider landing zones of obstacles, and establish supply routes before German armored forces could counterattack. The plan included delivering bulldozers by glider as part of the initial airborne assault. Mission Chicago, departing Aldermaston Airfield in southern England, consisted of 52 gliders carrying troops and equipment for the 101st Airborne Division. One glider carried a CA-1 bulldozer, packed in a specially modified cargo bay with reinforced floor and additional crash protection. The glider cut loose at 4 a.m. over Drop Zone E, descending through darkness toward Norman farmland that intelligence photos showed as flat fields suitable for landing. The photos were wrong. The fields were crisscrossed with hedgerows, ancient earthen walls topped with thick vegetation that divided Norman farmland into small enclosed pastures. Worse, German forces had planted thousands of posts called Rommel's asparagus throughout likely landing zones, sharpened stakes designed to impale gliders on approach. The pilot saw the obstacles too late. The glider hit a post mid-fuselage at 65 miles per hour. The wooden pole punched through the floor, drove up through the cargo bay, and erupted through the roof before snapping. The impact broke the glider in half. The forward section with the pilots tumbled across the field, coming to rest against a hedgerow. The cargo section, containing the bulldozer, slid another 100 feet on its belly before wedging against 2 Rommel's asparagus posts. When engineers reached the wreck at dawn, they expected total loss. The glider had literally broken apart around the dozer. The cargo compartment no longer existed as a structure, just shattered wood and torn fabric wrapped around 5,000 pounds of steel. They cleared debris, examined the machine. The blade had bent slightly from impact. One track showed damage where a wooden post had struck it. The engine hood had multiple punctures from wood splinters driven through it like arrows. But the frame was intact, engine bolted solidly in place, hydraulics holding pressure. They replaced the damaged track section with parts from another wrecked glider, straightened the blade as much as possible without proper tools, checked fuel and oil. The dozer started on the first pull. Within an hour, that bulldozer was clearing Rommel's asparagus from surrounding fields so follow-on gliders could land safely. It worked continuously for 3 days, clearing obstacles, filling shell craters, grading supply routes from the beaches inland. The bent blade actually improved its performance in soft Norman soil, creating a curved cutting edge that penetrated more effectively than the original straight design. Throughout June and July 1944, CA-1 bulldozers, delivered by glider, played essential roles across Normandy. They cleared beach obstacles under fire, expanded landing zones while combat raged around them, constructed the emergency airstrips that evacuated thousands of wounded soldiers who would have died waiting for hospital ships. Many dozers worked for weeks beyond their expected 72-hour service life, operators performing field repairs with improvised parts, keeping machines running through mechanical ingenuity and desperate necessity. Yet despite this combat record, despite proving themselves in Burma, the Pacific, and Europe, the CA-1 bulldozers never received recognition. There are no monuments to airborne construction equipment. Military histories focus on infantry and tanks, on dramatic battles and famous generals. Engineering equipment appears in footnotes, if it appears at all, catalogued as logistics detail rather than combat necessity. The men who designed these machines, who tested them, who manufactured them, who flew them into combat and operated them under fire, have been forgotten by history. Maurice Zollinger died in obscurity in 1973. Clark Equipment Company never advertised their wartime contribution. The Army classified the specifications and employment doctrine until the 1980s. Today, fewer than a dozen CA-1 bulldozers survive in museums worldwide, displayed without context, labeled with basic specifications that reveal nothing about the engineering that made them possible or the operations they enabled. But the principles Clark developed didn't disappear. They evolved into modern military logistics doctrine, into air-mobile construction equipment, into the rapid deployment engineering capabilities that define contemporary warfare. Every time a helicopter delivers construction equipment to a forward position, every time engineers build an emergency airstrip in hostile territory, every time military forces establish bases faster than enemies expect possible, they're using concepts that Maurice Zollinger pioneered in 1942. The story of the CA-1 is the story of military logistics at its finest. Unglamorous, essential, effective. Sometimes the key to victory isn't better weapons or braver soldiers. Sometimes it's better bulldozers that arrive where needed, when needed, regardless of how violent the delivery. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.